Hello, everyone. My name is Val. I'm with GridGain Systems. I hold the position of lead architect, and I'm also one of the committers of Apache Ignite project. During my employment at GridGain, I did a lot of different kind of stuff. I started with development, spent several years participating in actual development of the core product. Then I moved to more like customer-oriented work. I'm working with our customers and users, helping them with technical challenges, and helping building applications, actual applications based on Apache Ignite and GridGain. And I like to think I have certain experience in distributed systems in general and Apache Ignite GridGain in particular, as well as building the applications based on these kind of systems. And today I'd like to share some of that experience, and in particular I want to talk about different pitfalls and techniques to avoid and work around those pitfalls to get the most of the distributed systems in terms of performance and scalability. So starting with basics, this is like a typical architectural diagram of a distributed system that stores data. So we have multiple nodes that are used as a data storage. The data is stored on those nodes, and the data is distributed across those nodes, meaning that every node actually stores a small portion of the data, and this allows you easily scale out your system, like adding more nodes to provide more resources to the system, provide more memory to the system, or more computational to your system if computational resources are not enough to do the processing, for example. Right, and on top of the actual storage, you would have different APIs to interact with the data. The actual API used would differ from one system to another, like data grids typically provide key value APIs and different compute capabilities. In memory databases, they're usually like SQL oriented and provide kind of comprehensive SQL support. Apache Ignite has all of them, both key value, SQL APIs, computations, also transactional support, and some others. And by the way, this particular diagram is for Apache Ignite, as well as all the examples that I'm using throughout the presentation, all the like specific terms that I'm using, they are from Apache Ignite. However, like the general concepts I'm talking about, they are applicable to any distributed system, or at least in one form or another. So if you are using something else other than Apache Ignite or GridGain, any other data grid or in distributed database, you would probably find some useful information as well. So the main challenge with a distributed system actually is the fact that it's distributed, right? So it's essentially a bunch of computers connected via the network, and the network itself is used to coordinate between nodes, and there is a lot of communication happening, and that's an overhead. So on top of the performance improvements that you get from scaling out, you get an overhead provided by the network. And to better explain that, I have this kind of analogy that I like to use to explain why this is a big challenge. So these are two cavemen who, for some reason, wanted to bring like a huge piece of stone to their cave. So the guy on the left just found a huge boulder on the ground and tries to push it, and obviously barely succeeds because it's very heavy. The guy on the right is more lucky. He found this circle-shaped kind of stone, so he can just roll it and progress much quicker. So those two guys, they probably don't even understand what's going on and why there is so much difference between those two approaches to the same problem, right? But we all here know that the reason for that is the friction between the boulder and the earth, right? So in the first case, there is a huge amount of friction, the boulder is heavy, and it's really hard to move it. In the second case, there is much less friction, so it's much easier to move it. So it kind of looks like there is a very simple, straightforward formula to that, to how they optimize this process. We just basically minimize the friction, and we're good. And that's not quite true, because if we minimize it to 0, we will not be able to move the second stone. Actually, it will just roll but not move. So it turns out that it's not a matter of minimizing the friction, but it's rather a matter of applying a certain amount of friction so that it's enough to move it, but not so huge so that it's hard to move it. And it's also a matter of properly applying it in a certain way so that we're not doing too much work. And in distributed systems, we have the same exact thing. And the network is our friction there. Because network is essential. There is no distributed system without a network. It cannot work without it. However, network communication itself is very expensive. And if your application, if your API invocations that you use in your applications, the queries that you execute in your applications trigger too much network communication, you just get very bad results. You get a non-scalable system, you get a very slow system, and it doesn't really work. So distributed system doesn't really provide you any advantages because of that. Basically to understand how to work with that and how to make sure you don't go into those bad situations, the main thing to understand here is how the data is actually distributed across nodes. That's an essential part of any distributed system. Every distributed system has its own way to distribute the data. And I will go through that using Apache Ignite as an example. So let's answer this question, right? So whenever we do some operation on the cache, for example, right, we're doing a put, providing a key value pair. Data is distributed, right? So this entry will be actually stored on one of the nodes, on node 1 or node 2. So we have to somehow choose, the system has to choose which node to use for this entry, so that we can choose the node where to send requests to. So in Apache Ignite, we actually do this in the following way. So we have every cache will have multiple partitions, first of all, right? So the data is split into partitions. Every partition is kind of a bucket for entries. So for example, you have one partition with like 4 entries there, and there is another partition with some other entries that are not related to the previous one. And then those partitions would be distributed across nodes. So if you have 2 nodes and several partitions, you will have certain distribution. So there would be some algorithm that decides how to do that. Like for example, in a very simple example, there would be like round robin kind of way to do that. We have partition 0 on node 1, partition 1 on node 2, and so on. Right? So this brings us to kind of a 2-step process of the mapping between the key and the node. Right? So whenever we do something, whenever we do any cache operation, we first have to map this key that we are using for this operation to the node where this key is stored. So the first step would be to map the key to the partition. That's a very simple hash function usually, like taking the hash code of the key, applying modulus function, and basically just selecting a bucket for this entry, for this key. And this step is constant, by the way, which is pretty important in certain scenarios, because the hash code obviously doesn't change, never changes. And the number of partitions also never changes. So it's a constant number of partitions. So this mapping does not depend on the current topology, and it doesn't depend on how many nodes you have. The second step is dynamic. It's much more complicated, actually, and it's dynamic because we have to recalculate this mapping every time we add more nodes or we remove nodes. In Ignite, this is encapsulated in what we call Affinity Function, so it's kind of a component of the system that we can use every time we want to know where a particular entry is stored. So if we want to do a put, for example, as in our previous example, in the previous slide, we basically would just consult the Affinity function, we would invoke the Affinity function, and ask where this key is stored. And for example, if it tells us that this particular key is stored in the partition 2, which is on node 1, we would go to the node 1. We would never go to node 2 in this case. So now, how do we actually use that information, that knowledge of the data locality, to improve the performance and scalability of the applications? There are basically many techniques and approaches to that. I'm going to talk about collocation. Collocation is kind of an umbrella term for different kind of things. But all of them, in general, mean that you put so you know where the particular entry is, and you put something else next to that entry, on that node where this entry is stored, so that you don't move this entry. And the most obvious example of that is collocated processing. It's fairly straightforward. Collocated processing basically just means that instead of fetching the data to the processing node where the processing happens, you move the processing to the data, to the server nodes where the data is stored, right? So you can think of it as an alternative to like traditional client-server approach, where you would go to all the nodes, gather certain subsets of data, move them to the processing node, do some processing, and then probably update something back. In the collocated processing approach, which is shown on the right, you would instead send the closures, like a computation, lightweight requests, to those nodes, execute those computation closures on those nodes, and then gather results, like partial results on the client node, and do the final reduce step. So, simple example. Very typical use case of updating an account balance. So we have an account object, which certain metadata for that account, like first name, last name, like address or whatever. It can be pretty big object. And there is also the actual balance value of the current, which represents the current balance for that account. And we want to update that. Like the account owner swipes the card somewhere and we want to subtract $100 from the account. So how would we do that with a traditional client-server approach that was shown on the left picture on the previous slide? We would actually read the account data to the client node, update the balance there, and then write it back. And the code is shown on the right. So functionally, this code is perfectly fine. It's going to work. So it would provide the correct result. It would properly update the balance, assuming that you wrap it properly in transaction and everything else. It would be atomic and consistent. So nothing is wrong with this code from functional standpoint. However, from performance standpoint, there are at least two problems. Problem number one, we have to do 2 round trips here. We have to go to the server node and back when we read the data, and we have to go to the server node and back when we update the data. And the second problem is that every time we do this round trip, we also have to fetch the whole account object, which can be really big. So this kills the performance right away. And if you think about it, I mean, it's not really what we need, right? Why do we need all this data about this account on the client node? Why do we even need to know what is the current balance there? What we really want is we want to tell our database to update the certain account with a certain ID and subtract like $100 from there, and then get the confirmation that that happened. That's all we want to do. There are, obviously many ways to do that. That's a very simple example. But like in JCache, in any system that implements JCache, there is entry processor API, entry processor interface, and invoke method, which are used in conjunction. So basically, it does exactly what I just described before. So instead of moving data back and forth, you provide an entry processor implementation, which implements the actual logic of the processing that you want to do there. And the entry processor would be sent to the server node where this entry is stored and would be executed there. So instead of doing 2 round trips to the server node and back, we do only 1. We're doing single cache operation here. And we never transfer the full account object through the network. So again, from functional standpoint, this code does exactly the same. It updates the account balance. But from performance standpoint, it would provide much better results. It would be much better from the latency standpoint and from throughput standpoint as well, on the same amount of resources. All right, so in previous example, we collocated some computation with a single entry that we have in the database, that we have in cache. But sometimes we also may want to collocate 2 entries together, or multiple entries together, basically creating like groups of entry logically connected to each other, although they are like physically stored separately in the cache, right? I will show this with an example again. This is actually like a real use case. I was working on that with one of our customers, with one of the big banks. Use case is the following. This is basically like credit card authorization use case. So every time someone swipes the card, we create a new transaction object like shown on the left, which has an amount, like a store name, where it happens, and the account ID. And before storing this transaction ID in the cache and basically accepting the transaction, we want to authorize it. And we want to do this in real time. And to do the authorization, we basically need to take like 30,000 latest transactions for the same account, go through all of them, calculate certain authorization variables, and then make a decision based on that. So by default, all those transaction objects are separate. They do not depend on each other, and therefore, they are randomly distributed across nodes. So you will have transactions for the same account stored on different nodes. And that obviously creates problems. We cannot do collocated processing now because there is no single node where we can send this processing to execute, right? So we have to fetch all the transactions for this account to some other processing node, do the processing there, and then make a decision, which is basically our traditional client-server approach. To avoid that, to avoid the problem, we need to make sure that all the transactions are stored on the same node. Then we would, and also we need to make sure that we can send the computation to that node. This way, we would be able to send the closure there and do the processing where the data is. So that's how it's done in Ignite. So let's come back to our affinity function mapping that I was describing before. So we had like two-step mapping there, right? To solve this problem that I was just describing, we actually just, there's actually a pretty like elegant solution, I think. We just add another step here. So before mapping key to partition, we convert this cache key, which is unique for every entry. This is like a primary key, right? We convert it to affinity key. And then we use the affinity key as an actual value for the affinity function. So the affinity key is passed to the affinity function instead of the cache key. And affinity key doesn't have requirement to be unique. It can be the same for multiple entries, right? And in our case, I mean, obviously, pretty natural, we want to use the account ID as this affinity key, right? So this way, so if every transaction is mapped to the same affinity key, which is the account ID in our case, we make sure that it will be mapped to the same node. The actual algorithm doesn't really change. We just add this additional step here. And then we also will be able to use the account ID as for the computations, right? Because we will just ask our affinity function where the data for the account ID is, and would send the closure there. So that's how it looks in code. So again, in Ignite, we would just basically create the transaction key class with two fields. The first one would be the actual transaction ID, which is our unique identifier of every transaction. And the second one would be account ID. And the account ID we want to use as affinity key, so we mark it as with affinity key mapped annotation. That's all you need to do here. Ignite will figure out everything by himself. So it would use this annotation and would use this field as affinity key. So every time you save something in the cache with this, with the instance of with this class as a key, providing the account ID, it would be mapped based on the account ID, not based on the transaction ID. So everything with the same account ID goes to the same node. And then, like shown in the code on the right, you would use special API that is also provided, like Affinity Run, for example, where you basically just provide the cache name where the data is stored. You provide the account ID, which is our affinity key, and you provide the closure or a lambda, which will implement the actual processing logic, which would iterate through all the transactions and calculate all those variables and so on. So this will be executed on the server node where all those transactions now are stored, and all the data would be local to that computation. Again, we avoid network communication. Again, we avoid moving data around, moving data back and forth, and gain a lot of performance improvement from that. All right. So far, I was going through examples that involve using key value APIs, right? But what if you use SQL? Like many databases, they provide SQL support. Ignite also does. So what if you use only SQL queries to access the data and you don't ever use key value APIs? Sorry. Does collocation affect you somehow? Actually, it does. And it can be even more tricky because here you doesn't work with actual keys, and it's less obvious how the data locality affects the execution of the queries. So let's go through a couple of examples here as well. So the same data model, we have our transaction objects. Although let's take a step back and assume we did not do collocation, right? So like just imagine we don't have this authorization process and we just save those transaction objects as we create them, and we don't care about collocation. And then we execute the query like this. So basically we just want to calculate the average transaction amount for a certain account. Let's investigate how the query will be executed, and I will also compare how it scales, and basically I will compare the execution with a single node and multiple nodes. So by default, there are no indexes unless you explicitly create them. If there are no indexes, you have to scan the whole data set to execute this query. Like for example, you have 300 transactions in your database, in this table, across all accounts, not only for the account that you're interested in, but for all the accounts. We have 300 transactions. With single node, we would go to that node, scan 300 transactions on that node, and we'll get the result. If we scale this out to 3 nodes, the data set is now split across those nodes. So every node has like 100 transactions. And now we can broadcast the query across those nodes, execute it on every node, and do the scan on every node. And every scan would involve only 100 entries, and you can do those scans in parallel. And of course, it scales out. You can do this in parallel, so latency goes down. You get latency improvements. You get capacity improvements as well. Capacity here, by the way, is like the maximum system throughput, like maximum number of queries you can execute concurrently in parallel without compromising the latency, right? So capacity also increases because on every node, you save certain computational resources, and you can use them for other queries that are executed concurrently with this one. But I mean, this query would probably never be executed without an index. You would have an index on the account ID field, which will obviously improve the performance of the query itself, because it will use the advantages of the index search. And let's check how it would be executed in this case. Index is, as we all know, usually at least, basically like a sorted tree structure. And with a single node, we would have this tree structure along with our data, right? So instead of scanning the data, we would go to this tree structure and search there and look for the entries we're interested in based on the value we provided. With multiple nodes, we would have multiple those structures, instances of this structure. So every node would have a subset of data and would also have an index which corresponds to that subset of data. So not only data is distributed, but the index is distributed itself in the same way. So now when we execute the query, we broadcast to all the nodes and go through all those tree structures to look for the entries we are looking for. And the algorithmic complexity of the sorted tree search is, as all we know, a logarithm. So for example, if we have like 1 million entries, we would have to do approximately 20 iterations through the tree to find the entries. That's in the worst case, of course. Now, what happens if we split the data? If we split the data, we get actually something like this. So we have much less data on every node. But the amount of iterations we have to do through the tree structure, through the index, is pretty much the same. You would not even notice the difference. So the latency of this query is going to be the same. And on top of that, the capacity doesn't change either. Because, I mean, basically, every node has to do the same amount of work, regardless of how many nodes we have. This is like a no-go, right? Because we just created a completely non-scalable system. Although it looks like we didn't do anything wrong, right? We just created a data model, put some data, and executed the query. But once we executed this query, the system stopped being scalable. We can add like 100 nodes here. Nothing changes. Latency is the same. Capacity is the same. Almost the same. How do we solve this? And again, collocation helps us here. So let's try to collocate. Again, the same exact way like we did before. We will collocate by the account ID. And the point of this collocation here is that once we do the collocation, when we parse and analyze this query, we can figure out that all the data that is required for this query actually belongs to a single account. And we also know that we now collocate by account ID. Our account ID is our affinity key. This is like, we put this into the configuration. So now we can actually call the affinity function, figure out on which node all the data for this account ID is stored, and send this query only to that node and execute it there. And here's what happens. So now we can add more nodes, but we still use only one node, the first one, for example, to execute this query. So when we execute like a single query in the system, other nodes are just idle, and they can be used to execute other queries in parallel. So this makes it much more scalable because by adding more nodes, we're increasing capacity of the system. We're increasing maximum throughput of the system. So if like you have, if the load on your system increases, you can just add more nodes and it will handle more queries in parallel. Latency doesn't change in this case because we always use the same single node to execute the query. However, this is probably fine. Most cases it's okay because we're already using index and latency is most likely very good at this point. But this way we achieved the scalability of the maximum throughput, which is what we're looking for here. All right, and finally, I want to talk about joins. So when you work with SQL, you would most likely use joins in some of your queries. And collocation for joins is also very important. And here's why. Let's go through this data model. Again, pretty straightforward data model. We have a country table, right, which represents countries like Canada, India, others. And we have the city table, which represents different cities. And they have one-to-many relationship between them, having the country ID in the city table as a foreign key, right? So again, by default, if we don't do any collocation, we would get the random distribution, like, for example, shown here, right? So all the cities would be randomly distributed. Some of the Canadian cities would be on the node 1. Some of the Canadian cities would be on the node 2. Same happens to Indian cities, of course, and to all other countries. And when we do a join, we will broadcast it to all the nodes, and now we have to reshuffle the data. Because when we execute this join on the first node, for example, we will get Toronto, Calgary for Canada, but we will not get all other cities. So we have to somehow figure out how to find all those missing cities that are not on that node near Canada and bring them there, and then they execute the join. Same happens for India, and this creates a lot of communication between nodes. So we basically have to reshuffle all the data and move it around to make sure that the result is correct. This is very expensive. This is called a non-collocated join, which is supported by Apache Ignite and by other system databases as well. And it's supported mainly because there are cases when it's not possible to predict all possible joins, especially like in the analytical use cases, where like ad hoc queries are executed by users and you, physically cannot predict everything. However, you just need to make sure that these queries are rare, first of all, and usually developers do not really care about this kind of queries. And there are certain queries that are executed more often, and they're more important from performance standpoint, and that's where you collocate. Because once you collocate, like let's collocate it first, right? So let's do the collocation. So our country, for country table, we don't have to do anything explicit because country ID is our cache key there, and by default, cache key is the same as affinity key. So this one would be just distributed by default. This is fine, like country ID 5 goes to node 1, for example, and then all the cities have to go to the same node as well. So we would have, again, like a city key object or something like that, or we provide this. We also can provide this in the configuration or in DDL statements when you create tables with SQL. So we just basically need to make sure that the country ID is used as the affinity key, and all the cities with the country ID equals 5 would go to the same first node, exactly where this country is. If there is a city with some other country ID, that can go to other node. We are okay with that. We just need to make sure that all the cities belonging to the same country are in the same node, and they're also on the same node where the row for this country is. Once we achieve that, we get the distribution like this. So all the Canadian cities are on the same node next to Canada, all the Indian cities on the same node next to India. So once we get this distribution and we execute the exact same query, we can just broadcast it across the nodes, execute it locally on every node, and those joins would provide the correct result right away. We don't have to move anything around, we don't have to reshuffle the data, and we get much better result from performance and scalability standpoint. So all these examples, I think, like, kind of give an idea why collocation is important and why all the understanding of how data is distributed and understanding of data locality is important for developers who work with distributed systems. Like in this latest example, for instance, it's a very good example, I think, because in both cases, there is no much difference, right? We had the same data model. We had the same data set. We executed the exact same query. We probably had the same cluster, resources, everything, but we get completely different result. The performance of this collocated join would be probably orders of magnitude faster than the performance of the non-collocated join. And so yeah, as I said, I think this example, as well as other example, they kind of give an idea why this is important and why you should always keep this in mind and make sure you use these kind of techniques when working with distributed systems. That's actually all I have.